Good morning, all. This is Mark Anderson. I'm going to be talking to you about evaluating and exploiting existing data, gold or garbage. If you can hear me, put your hand up on your control panel just to make sure we're getting through. Thanks, Kevin. And Michael, Molly, etc. Okay, great. So it's working today. Awesome. I'm actually speaking to you from my winter home in Florida, which is good because in Minneapolis, it's below zero and they just had 5 to 8 inches of snow. So I'm happy to be talking to you here from Florida at a distance. It's wonderful. My background, for those of you who aren't familiar, is professional chemical engineering. I'm also a certified quality engineer, and my current position is engineering consultant at Stadys. Over the years, I've done quite a bit of work trying to deal with existing data. And I'm happy to say that I've actually had some pretty good successes from time to time, but quite often it's been disappointing. But it's definitely worth a try. So that'll be my mission today, is to try to give you some ideas on what you might expect, and whether it really is going to be useful or it's just a bunch of nonsense and happenstance. So I'll go ahead and start the show, and we'll begin our presentation. So again, welcome, and I do appreciate you staying on mute throughout the presentation. At the very end, I will address any chats that you type in and possibly open up the mic. However, with a group this large, the best thing is if you make a note of a question as I go through, possibly the slide number, and then follow up afterwards with an email to me, mark@stadys.com. That'd be great. And then afterwards, this presentation will be posted, the slides as well as a recording here at this website, which is 3w.stadys.com. Just go there and click on the webinars and you'll find it. So one more time, just to make sure that we're getting through here, press that raise hand button if you're with me. Great. Yvette, Marissa, awesome. Alan, thank you very much. So I'll just call a few people out, but obviously statistical sampling works really wonderful for this, because I'm going to make a big assumption that if I ask this question and 1 or 2 people put their hands up, I already have a pretty good idea what's happening, that is probably working overall. And if there's issues, it could be something at your end, but no worries, we've got the recording posted. All right, so here's my talking points, is that we've made it really easy with Stadys software, and I'm actually going to be using a newer program that we just came out with called Stadys 360, which is a superset of the package that probably most of you are familiar with, which is Design Expert. And pretty much anything that I show you, even though I'm using Stadys 360, will be available also in Design Expert. So we've improved our ability through an import data function to make it easy to bring in, and it'll become even easier in the future with a direct Excel import that's in the works. So given that, why not try gleaning some gold from an existing process or product? What's cool about our software is that it not only can work with process type factors like time, temperature, agitation rate, and things like that I'm familiar with as a chemical process development engineer working in R&D, but it also can work with data that is comprised of ingredients or components in a mixture that has a fixed total. And this is really useful for the chemists in the group. And we've got very powerful tools for importing that information and then assessing it. So what we want to do first after we bring the data in is use Stadys' powerful evaluation tools and look at things like variance inflation factors and leverages, aliasing, and things like that to really decide whether we've got a chance or not. But I have to warn you, be ready for existing data to be garbage. And then we get this garbage in, garbage out, or what we used to call GIGO type syndrome. So before you get too far into the analysis of the existing data, do an assessment and see what's going on, how well it's actually laid out. You never know, it might be pretty good. Every once in a while, and I've seen this happen, and I'll bring up a couple of examples, you get an immediate win and it's at virtually no cost. So wouldn't that be nice? But unfortunately, more likely, it might be this guy go garbage in, garbage out. And in that case, you'll need to go to some sort of designed experiment. However, at least the time that you've spent on the existing data will provide some insights on potential cause and effect relationships, and that might help you do a better job of a well-designed experiment. So that's my premise here, and hopefully you'll see kind of both sides of it, the pros and the cons, as I work through, some issues here. So let's start off with the STADI software import and evaluation tools, and I'll show you how that works with a case study that's not very good. It's more garbage than it is gold, but it's a classic. And so we'll start with that. But again, to kind of set the stage here of why we're talking about this, it's very frequently asked question that's coming in, and this happened to be one from a section head of materials and testing development, that in many cases, they want to model results from existing experiments where you haven't actually done a planned design of experiments. However, you have the ability to separate the data into continuous variables and responses. So the question is then, can we take existing variables and add, up a model that is comprised of interactions and squared terms and things like that? And can we subsequently plot these on the STADI software? And the answer is yes. However, we may not really want to get too far with that if it's not very good data to begin with. So it's easy, but is it going to be productive? Yes, with the current versions of STADI software, Design Expert and 360 do make it far easier than ever before to bring in these results. So let's take a look at that. We'll show how you can simply press the import button, and coming soon, you'll be able to import directly from Excel. Then with a little bit of work to identify, what the rows and the columns are, off you go. So let's take a shot at this. I'm going to toggle over to the newer product that STADI's just released last fall. It's called STADI's 360. It really is Design Expert supercharged with some key features. The one that I think is most exciting to a lot of people is we now have a script editor for Python. So you can extend the utility of the Design Expert core very broadly. So I like to think of 360, being a vision where we can expand our horizons, and the big expansion can occur through a tie-in with Python scripts. There is also some features that can help you do computer-aided design and analysis of experiments, where the computer simulations are producing deterministic results, and we have some special designs built in that are called space filling designs, Latin hypercube, and then we have an optimal space filling option. We also have on the back end for the analysis of deterministic data, something called a Gaussian process model, or GPM. That is covered in other presentations, so I'm not going to get into it. My mission today is to talk about how we can import existing data, and I'll be featuring this tool called Import Data. So what I did many years ago is I wrote up a tutorial on what I called happenstance or historical data. Now, in recent times, I've tried to avoid, talking about happenstance, quote unquote, or historical, and rather using the word existing data to be less negative about, what the quality of this might be. So my terminology has changed a little bit with some coaching from my colleagues like Martin Besseter, not to be so dismissive of it. However, my experiences were kind of poor, as I'll explain as I go along, being steered to using, existing data. So I have a little bit of bias against it, but I'm going to try to overcome that. Nevertheless, this particular tutorial is one where the historical data, it really is historical data, really isn't very good, but it's a classic study that was done by a fellow named Longley. And back in the day when we didn't have very good computing facilities, this would be a good one because of the tremendous correlations of the inputs to see if your regression engine was working properly. Because if it didn't go out to enough decimal places, the round off error would begin to accumulate. So this became kind of a test set of data that was good way back when, when we just had mainframe computing. So I took that, and years ago, I put that into Design Expert and was able to, learn some interesting things. And then I wrote that up in the RSM Simplified book early on, just to kind of explain what I'm talking about today, that you have to be careful to evaluate the quality of the data that's coming in before you start assuming you can use the results that come out. So that's the background of it. You can go back, and if you have our software or you trial download it, you can get it. Then if you're interested in this topic, then definitely go back into help tutorials and pull up this historical data. There's two parts to it, and follow through with that. What I'm going to do is I'm simply going to open the data file, and this relates to data from US government unemployment, as noted in this note, and I'll pull up the data on the screen. Now I just want to check, and I'm going to put the hands back down. Are you able to see a display of the data showing the prices, GNP, and things like that? Okay, people are raising their hands. Very good. And of course, when we look at this, we think, oh, this is pretty good. We ought to be able to do something with this and use it for econometric purposes. Obviously, we'd want to, have more than just 16 rows of data, but maybe it could be useful. So what I'm going to do, though, before we take a look at this and dive into it, is I'm just going to show you the import feature, and I'm going to recreate this Design Expert / States 360 file by clicking this upper left corner and then right-clicking over this highlighted area, and I'm going to copy with headings all this data. Then I'm going to go into Excel. I'm going to create a blank worksheet, and then I'm going to paste it in, and I'm just going to do Control V, to paste it in as a shortcut. Okay, now I'm going to right click over it, and I'm going to put it in onto the clipboard. So I've copied it now. Then in States 360, and you could do this in Design Expert as well, I'm going to close this design, and I'm going to click this import data function. Now I'm going to paste it. So now we have it pasted in, to this clipboard. And by the way, on the left-hand side, you might notice there's something called blank spreadsheet. That used to be how we would have to do it. We would have to create up a dummy design. It was very laborious. If you haven't gone to version 13 of Design Expert or gone to the States 360, this would be one good reason to make sure you get that upgrade. Because now what we can do is we can systematically doctor this up a little bit. I'm going to click this first row and I'm going to delete it because it really doesn't do anything for us. The second one, of course, is the names of the variables. This row I'm going to call units, right? Now we already have a number on the left-hand side. So I'm going to take these first two columns that say standard and run that I exported out of Design Expert / 360, and I'm going to delete those two columns. All right, we're not quite done yet because we need to tell the program, the States software, what are the inputs and what are the outputs. So I'm going to first say A, B, C, D, and E, and F are numeric factors, right? And then for this last column, I'm going to identify that as a response. And at this point, I should be good to go. And you can see it's come right back again. All right, so this is my demonstration of how you can take, any set of data, if it's in an Excel spreadsheet format, and you can bring it in, very easily using this import data, and in the future, even a direct import from XLSX type files. All right, so that's a little demonstration. Now, what I want to do is begin to evaluate this data. And the first thing you can do is click this evaluation on the left-hand side. And I'm not going to try to fit a quadratic model to this. Normally I would. If this was process data, I would try that. But I already know it's pretty poor, so I'm just going to settle for linear and just see how that does for the results. And the first thing I'm going to see is that every of these inputs is extremely correlated with all the others. This is called the R sub I squared, other than D. And then taking that R sub I squared and converting it into a variance inflation factor, we see that the variance inflation factors are consequently very high and much more than we would recommend. Ideally, it would be 1 if you have an orthogonal matrix like a 2-level factorial design, and above 10 are really cause for concern, and above 100 are cause for alarm, and we see some that are, in the thousands. So you can begin to see the problem right here. But let's say that you decide to press ahead. What I would do next is look at the graph columns. And first of all, what you see on this color-coded correlation grid is that it's pretty much all red. That means everything is highly correlated with each other. Obviously, if you try to correlate something with itself, it'll be totally correlated. But when you see a factor like A also almost exactly correlated with B and other factors, that kind of tells you that we've got a problem. And this pattern here I refer to as the picket fence, because I imagine that this would be, like the top of a picket fence, and you're going to try to put a model in which would be a planar surface, like a piece of plywood, and you would try to balance that plywood across the top of this picket fence, and of course it would be very, very wobbly. And it turns out that it's really hard to get, a good model out of something like this. I won't go any further with this because it's really garbage, but if you're interested, dig in on this Longley data, and ideally you would have our software in front of you, and you'd be able to go to this tutorial and see what happens further on as you try to fit this response. Another thing would be if you pick up the RSM Simplified book, I detail this particular case and the issues that are involved with that. So that's a starting point. I'm going to go ahead and put the hands down. If this gives you a good idea of the capability of the software to bring the data in, to be able to evaluate, what you have, to graph it, and so forth. If you're good to go from here, go ahead and give me the thumbs up or some kind of signal that I'm on the right track. So now you guys are empowered to be able to try this with your own data and see what happens. And by the way, if you try this, I'd be curious to hear from you. So again, don't be shy to follow up either right after this presentation or follow up later when you've tried this. And I'd be curious to see what you get, because what I'm especially interested in is if you're able to have some success with using this feature of import data, and the data isn't so bad and you do get a win out of it. I'd love to hear about that, because as I mentioned, I have this little bias or chip on my shoulder against using existing data and in favor of doing proactive design of experiments. So you can help me become more open-minded if you would send me any successes you have. So I did go back, and over the years I was able to do better and find a few things that did work. And so I'm going to share some success stories here to give you a more positive spin on what's going on. Before we do though, this slide this next part is going to be actually the potential problem. So I got ahead of myself here a little bit. I guess I can't help myself, but give you some cautions about this before we get into the success stories. So I'm just kind of quickly change this little agenda here. Okay, so now what I want to talk about is potential problems, and then the success stories, the best for the last. So here are some things that you have to watch out for straight away that could be problems. And one of them would be having inconsistent data that's sort of going up and down all around. It varies quite a lot over a period of time. And it could be because standards have been modified. You're dealing with plant process data. Um, they've shifted the process to meet new specifications from the customers. The instruments have changed. Calibrations are drifting. New operators, raw materials are constantly evolving, and there's just so many different things, seasonal effects, and much of what is causing this is unknown and it's not recorded. So this gets me to my story and why I ended up being a little bit negative about using prior data is, as a certified quality engineer, my R&D boss sent me down years ago to work in a manufacturing plant. And as soon as I arrived at the door, the plant manager said, "Oh, you can experiment as much as you would like, Mark, but only so long as you don't change anything." It's like, oh, I'm stumped. So the next thing they would do is they say, "Well, look, we've got these drawers full of quality control data, and we know that you've got access, to a powerful, regression program. And we've heard wonderful things happen from computers, and we're pretty sure that you could crank in all these numbers and come out with some kind of gold dust at the back end." And so what happened was I would have to try that. And I actually got pretty good at regressing this quality control data and predicting what would happen last month. Ha ha. Because what good does that do? That's just kind of characterizing what happened. But if I try to use it to predict what would happen in the future, it didn't work. And so what I would do oftentimes is hold back. So I would say hold back from the existing data 10% of it, and I would see if the 90% predicts the 10%, and it didn't. Most often it didn't work at all. It was just nonsense. And why? Because of the inconsistent data. That could have been it. Another big problem with existing data, especially plant data, is the factor ranges are very limited. Obviously, they're trying to control the variables, and they're trying to meet a very tight specification. And so you don't have much range to work with. It doesn't generate a signal. You have very small signal relative to the noise in the system, and you're just unable to see anything. And a good example of it would be shown here, where we have a very highly controlled input X, and then the response is varying, of course. And trying to get a fit of this data is going to be very difficult. Now, if we were able to take the production offline and create potential off-grade on the high and low end of the Y response, we would then have a much bigger driving force that would give us a strong signal for the noise that is consistent throughout, and we'd have a chance at it. But then you would be producing some off-grade, and usually they don't like that. So if we try to fit this data, this is kind of the picket fence problem I was talking about. You can see from this confidence band, that it flares out, and we're really extrapolating to the left and to the right. And so this line, could be wiggling all over the place. We can't really fit it very well. But now that we have, a much broader range and a lot more data, in this case, the confidence band is very tight. And so we would be able to, provide much greater precision, and it would be much more accurate. Okay, does that make sense? Yes? Go ahead and throw up a hand just to encourage me if you see the sense of the problem of having this limited range. Okay, great. Thanks, guys. Wayne, Stephen, etc. Okay. I'm very needy for positive reinforcement. You've probably noticed that already. Okay, so I've got a couple of problems already that I've stated. And then here's the picket fence example. And I think this one, well, it's actually not the one from, this is not the one from the econometric data. This is another example where we're looking at flow, temperature, and other factors. But the flow versus temperature, was very highly correlated. And then you see the VIF problem again here. Now this one is actually evaluated for a quadratic model, which is definitely pushing it too far. And so this is again an issue of controlling things so tightly, especially with automated process control. And this happens to be a continuous reactor. And when the temperature increases, the computer turns up the flow. And so that's why there's this high correlation and really bad variance inflation. And this makes the model fitting extremely problematic. So back in 2008, I put together a talk that was more negative than this one, if you can believe it. And I stood on the shoulders of my long-term colleague, Pat Whitcomb. And so it's a more technical webinar because he contributed to it, and we added on several other issues with the data, that you can have. So, do go back and you'll find this slide deck. It's not recorded, but you'll find a slide deck back on our website to dig in further on this particular problem and some of the other issues that I've got. And then one of my favorites of dealing with existing data is nonsense correlation. And basically, you have a problem of cause and effect relationship. You've got two things happening at the same time. And one of the jokes that I would always have is when I'd go down to the plant and I'd interview the process operators in particular, and sometimes even the engineers, I swear, they would say, the reason for the upsets is related to the phase of the moon. And particularly full moons, we notice that things really go bad. And I guess we can't totally discount that because there's some physical thing I can tell living here in Florida when I go to the beach, that the moon is having an impact. However, I really doubt that it was impacting our process at our plant. So it became kind of a joke that I would say, well, it's probably the moon that's causing this problem. But a more classic myth is one where the storks are delivering babies, and there's even some write-ups on this from the 20s and 30s. After World War I, there was a growth of population in Europe. They built lots of houses. The houses had chimneys. The storks came in and nested, and also life was going on, and people were having babies. And so there was a high degree of significance to the fact that storks were correlated to babies. And then they began making the jokes of the storks delivering the babies like this one here. So again, I have another case in this 2008 talk that's pretty funny. And it shows definitively that watching TV increases life expectancy. So check that one out. So lots of fun, nonsense correlation examples. Of course, if we do well-designed experiments and randomize the run order, then these time-related lurking factors will be washed out. We can also consider blocking, if there's some kind of changes going on day by day or lot by lot. I guess I have more problems. Hidden extrapolation. This one is kind of interesting. I picked it up from Montgomery, Peck, and Vining, Introduction to Linear Regression Analysis. And so this is more or less a quote from them and a screenshot that I took out of their book. And they're showing an original range for x sub 1 and for x sub 2, but although they form a square, the actual way that they collected this data or they ran this experiment caused them to fit within this elliptical shape, so they're correlated. And then they're trying to predict what's going to happen at this particular point, which obviously isn't a great idea. So I think that just graphically illustrates how it seems like you're staying within the range of the design space, but when you realize where your points are located, it's actually what they call a hidden extrapolation. So I thought that was interesting. And then again, of course, Montgomery, Peck, and Vining promote, planned experiments that will minimize the multicollinearity and even make it orthogonal where there is no correlation. And then also there's ways to create design spaces in Design Expert, for example, where you cut off the corners of this using multilinear constraints. And so you don't even allow this extrapolation. Another good thing about planned experiments is that you'll be careful not to have very high leverage or what they called wild points. And that would be like one time one of my daughters came back from the high school. She said, Dad, we're doing this little fitting in social studies of X versus Y. And we've got this whole cloud of points down here. And then there's one point up here. And they're fitting the line like that, right through that point. I said, is that right? They said, and I said, no, because you've got a leverage of 1 up here if you have only 1 point. And you never want to have that in, an actual data set. So I thought that was pretty smart for them to recognize, something was not right about this fit. But it was in social studies, so I guess we got to cut them some slack. All right, so that's what I meant to say in that little section was some problems, and then get into the success stories. Before I get into the success stories, I want to take a little poll, and I do see there's some questions coming in. And I'll go ahead, since we're at a little juncture here, and address a couple questions that came in from Vincent. Is the response column always an average, or how do you enter the possible replicates you could have? So what you're going to do is, if it's repeated measures, then you're going to put in the average. Like, we have a lot of variability in our analytical method, and so to overcome that, for every run or setup of our process, we measure it, let's say 3 times. In that case, you'd put the average in. Another example that is completely different is that we do a complete replicate of our process. We shut down the reactor, and then later at a random interval, we reset it up at the same conditions, run it out, collect the data. That would be what we call a replicate. And so this is kind of a very common question. I think if you look on our website, you'll see some discussion about that. In fact, I think there's a webinar that discusses that. So check into the website and there'll be more information. Would machine learning neural networks help in this case? Vincent asks. And I would say possibly. I mean, I had a call some years back from a 3M scientist, and they said they were using neural networks to, try to tease something out of existing data. I don't have a lot of experience with that, but what's interesting is the 3M scientist said, oh, by the way, we noticed when you fed in design of experiments data into the neural network, it like enriched the diet of it, and we got much better results. So I thought that was a good, example of where designed experiments are always going to be much, more productive for information. But I definitely would say, if you don't want to use the standard regression type modeling for mining data, do take a look at if you've got the programs to do the neural network and other approaches. Okay, so I'm just going to go ahead then and continue on with success stories, but my little question is, if any of you have had success stories, put your hand up in using existing data, whether it be neural network or some other approach. I'm kind of looking over the list here. I've got 58 attendees, and I do have some hands coming up. Bill Arndt, who's a guy that I've worked with in the past, has had some success. And I see some other people raising their hand. I think we've got Jennifer, Kevin. Okay, so we do have some successes. There is some hope. So why not? That's my thinking. I love to try things, and if it doesn't cost that much, give it a try. So here's some of the success stories that I had, and hopefully I'll pick up some more from you guys, that you'll send me some emails. Some years back, I was doing work with a company. I'm a little reluctant to say the name of the company, that was heavy into Six Sigma program. And they identified a group they called the Tiger Team that was tasked with finding the world-class DOE software. And it just happened that I was giving a presentation at a conference. I think it was a quality and productivity research conference, something like that, from ASA. And this Tiger Team leader attended, and he was very impressed with some tools such as propagation of error that we provide for response surface methods. So he told his management that they ought to pick out Design Expert and use our training for the DOE part of their Six Sigma. And therefore, I got involved with this, and I was teaching a class, And one of the students came in, and they were actually working on a problem that the CEO of the company had tasked them to work on a very high priority, and it had to do with a nuclear fuel rod binder. So it was pretty, pretty important, and I was a little bit nervous about, being called in on this. But I said, well, what have you got? They said, well, we've got this Excel spreadsheet, and we've got a series of ingredients, and they add up. I noticed when I did a sum column, every time it was like either 99.9% or 100.1 or sometimes 100% right on the nose. So I said, I think I can do something with this with a little bit of doctoring to get this all out to 100. And I can treat this as a mixture design. Okay, because we've got this data and we've got it in Excel. And so, and it's almost 100%, just a little off on some of the rows. And surprisingly, when I went into the design evaluation, it didn't look so bad for the variance inflation factors. It didn't look so bad for the graph columns picket fence. So then I said, why don't we try modeling this using Chaffee polynomial? And darned if there wasn't a sweet spot that came out that retained the strength of the rod, but at the same time, you were able to substitute with an environmentally friendly component. And so this really, demonstrated the advantage of taking existing data. It was kind of like the one shining beacon that I had for years and years. And it was my one hope that always, led me not to reject the possibility. So that was kind of standing alone as a success story for many years. But then more recently, just several years ago, I was again teaching a class and something similar came up. And this was fun because it was in Jamaica. And I was actually not too far from Kingston in Jamaica. And I was able to take a little side trip over and go to the Bob Marley Museum. And I really became, into reggae music. So here at my winter home, once, my 60% day is done, during that period, I might listen to just instrumental music for working purposes. But once the day is done, what the heck, I'll throw on that reggae music and get some Bob Marley going. And I might even have a beverage or two. So this is kind of a happy memory for me that I worked with this Jamaican client. And they had a domain expert that was on site. And they happened to be working on how to reduce aluminum that was coming out in these discard streams from their bauxite purification plant. And this form of aluminum is something called gibbsite. And here's the formula for it. And this particular gibbsite, they don't want to be losing that and throwing it out into the landfill. And there was various granulations that we could focus on, but he thought maybe the 30 mesh solids would be, something to pay attention to, and this might be the problem. So by happenstance, they had a variety of conditions that had occurred over time during the actual manufacturing. So they said, Mark, we've been taking this class and we notice how powerful the program is, for example, for response surface methods. We wonder if you could, maybe work on this a little bit. So I said, okay, give me the Excel spreadsheet. And just like I did with that nuclear fuel rod, I went back to my hotel and I worked on it. And darned if the results didn't confirm what the consultant suspected. So I've taken that data, I happen to have it, and I'm going to open it up. It's a file called bauxite. And let's see what we can make out of it. So now I'm toggling back over, and I'm going to close out what's up here. And I'm going to open up this bauxite. So this already has been imported, from Excel, back in the day. And so the first thing we want to do is see if we can evaluate this. Now there's a lot of data, and it's pretty hard just to look at it and figure out what the heck is going on. I will point out that under the summary, we'll be able to see, that there's just a number of factors that are listed here, and you'll notice, various meshes are factors here. And then for the responses, well, the main thing was this gibbsite, okay? So now the first thing is, as I mentioned, is to go to evaluation. Now this one, I'm going to go ahead and be hopeful that I could fit a quadratic to it. Then I'm going to look at the results. And never mind this fraction of design space, it's a sizing tool that you normally would use if you're doing a proactive experiment to try to get the precision of your fit, to within what you're aiming for, given the noise in the system. So we won't look at that because we've already got the data. So, not great. There's a lot of VAFs over 10. There's many over 100. But why give up before you start? Another thing that I like to look at is leverage, and that may not be quite so bad. You remember the problem that my daughter brought in where they had 1 point off to the right that had a leverage of 1. So there's some that are flagged here with stars, like this one here and so forth. But all right, well, what about graph columns? It's not all red like it was with the employment data. And let's say I look at factor A versus itself, of course, is totally correlated, versus B, the silica. It's not, quite as bad as a picket fence. Factor C, A versus C, and so forth. And then some of the factors versus others are fairly uncorrelated, and they have these lighter shades in the color-coded correlation grid. Okay, so why not take a try? Now, what happened here was it was kind of messed up. And the program is not quite sure, should it try to fit a linear to this or a quadratic? And the problem is you get negative predicted R squared. So when you see this, you might just go ahead and try the higher order model and then do an auto select, and it might come up preset with this AKE, EK information criteria corrected, which are President Martin Bessener, our Top Gun statistician, PhD level, likes because it's a good measure of goodness of fit. And going forward, and we can, create a model using this process that eliminates insignificant terms subject to hierarchy. So this is one way of doing it, and it ends up, with an extremely marginal model, but it does have adequate precision above 4, which is a good sign. So maybe we could do something with it. Now, just for argument's sake, if I create a new node here, and this one I'm going to do p-value, which is kind of, easier to explain, and I like doing backward. So I'm just going to, just because I like to try this, I'm going to do the same model fitting, but this time I'm going to shift it to p-value backward. See if that does anything different. And it takes out the most insignificant term, the next most insignificant term, and then it puts in any terms needed to support hierarchy. And in this case, I'm able to get better model, but it could be due to the settings as well. This is kind of indicates there's a problem with the data, because almost always, if you have decent data, doing it these two different ways will give you the same result. But if you have data that's kind of garbagey, you might try things a couple different ways. And I have an example of this on the employment data as well. So now we have one model that's shown here with the AICC forward, and the other model here that must be including some additional terms. And I'd have to dissect this. The adequate precision for this model is 11.8, but the model for the AIC forward is 12.1. So there's some indications actually that the AICC forward is better than the p-value backward, but it's kind of a mixed bag. But it doesn't really matter, because what we found either way is if you go to the model graphs and look at the perturbation plot, which shows you the effect of all the components all at once, all the factors, notice that E has this huge range to it and a big spread. And E happens to be the 30 mesh solids, which was what the consultant thought was going to be important. So there you go. Now, if I look at the p-value backward, AICC forward model graph perturbation, oh, it took E out of the model in that case. So I think I'm going to go with the p-value backward, which was all I had back then because that was before Martin started. And that was our win, was seeing under the p-value backward that potentially the 30 mesh did have an impact. And to be fair, what you're doing is you're using the combination of subject matter knowledge with this domain expert and data, which is very dicey. But together, it seemed to confirm that the 30 mesh solids were important, and they were able to later go back and they were able to pin it down and reduce the Gibbsite lysis. So that definitely is a success. So now that gave you a good, run through of some of the different issues that you might come across. Now, just as I was getting this talk together, something else came in. So at the very last minute, I put this in. I mean, literally, this came in yesterday. Because on Monday, I talked to this R&D lab manager, and let's see, I think he was a fellow from Barcelona, Spain, that had trialed our software. So I set up a little Teams meeting with him, and he explained what was going on. And I asked him if he would send me this data because he had just a meager set of data to work with. So I want to show you this because it turns out that if you have a set of data and it's not too terrible, you might keep that data and then augment it into something that could be useful. And we had a saying, I don't know if this makes any sense to you guys, but you try to make a silk purse out of a sow's ear. This goes way back. And sometimes you can do that. You can make garbage into gold. It's like alchemy. So here's the case that I just worked on a few days ago. I'll close this out. And this is an agricultural chemical process. Let's see if I can find it here. Ooh, where did it go? Hang on a second. I'm going to go over to Design Expert and open that up. This may not work quite as well as I thought. Okay, here it is. So what do we have here? Supposedly, this was a design that was done as a response surface method using our D-optimal. Well, it should have been, I can see already what happened. He put this in as categoric factors, and it should have been put as numeric, and they should have used I-optimal. So this was just kind of a beginning situation for this potential new user. So we need to be patient with that. So what I did was I went through and I actually made factors that were initially set up as categoric into numeric factors. And they had different responses. I think this first one might be yield. Anyways, it related to the yield of the process. So then I did my usual thing. I said, well, let's see how well it does to fit the process order of quadratic. And the first thing I noticed is that it was aliased. We couldn't fit all the terms in the quadratic. See, and so I'm not sure how this came about, but it didn't have, the full range of different levels of the different factors to be able to fit the quadratic. There just wasn't enough information. So I said, no problem, because we can take this experiment and we can use design tools, augment design, augment with additional runs. By the way, you can also modify the design space itself. You can shrink it, you can expand it. So there's tremendous tools, to do what I call making a silk purse out of a sow's ear, or making garbage into gold. And this one, I would do simply an augmentation of it. And then I would switch it over to I-optimal and just say, what do we need to do to fit this full quadratic? And it says, well, if you just add 3 more points and then maybe some extra ones, just to make it more stout, when in doubt, build it stout, and put this into a second block, and then some of these values can be rounded using the tool in Design Expert 13 and beyond. So we can round, each of these columns like that, and then we have something. And so this should be very doable then to go in and follow up by doing a series of extra runs. I think it's like 8 or 10 runs in a second block of time, and get that data collected, and who knows, maybe we'll make something out of it. So that remains to be seen. But anyways, the point being that you could take something that's already existing. I don't recommend that as a general rule, because I'd rather just start with a new design and never mind what happened before. But sometimes it's worth a try. My general experience has been not to use the old data because it's just going to pollute the new data. I had a situation with General Mills Chemical when I worked there years ago, and they were making this polyamide resin, and they had a bunch of off-grade because it had black specks in it. And then they took the off-grade with the black specks and they tried to blend it in to the new resin, and mysteriously the black specks multiplied. And it was like the cat in the hat had the red spot, and they kept trying to get rid of the red spot, and it just kept diluting and everything turned red. So taking the old and blending it in with the new is not always going to be successful. So to the extent that you spend time, just looking at what you already have, and it doesn't take too long, it's easy, why not try? And then once you bring it in, use the powerful evaluation tools in the Stati software and be ready for it being garbage. Also do the graph columns. Now you might just press ahead anyways, and who knows, maybe you would achieve an immediate win. And even though we had fairly garbagey data from the Jamaican bauxite plant, we were able to tease out something that was useful. So more likely though, it's going to be garbage in and it's going to be garbage out. So then either do an augmentation of it, but that doesn't really make a lot of sense if it really is garbage. But otherwise, just try to use what you have to point you in some direction and do a well-designed experiment. And by the way, one of the ways that this really easy and simple import function can be used is you can take data from other general stat packages, and you can export from there, and then using your Design Expert or a trial version of it, bring it into the Design Expert or Stati 360, and I think you'll see how much better Stati software is at evaluating and analyzing and modeling and graphing. So I found that that's a very useful tool to take something from other stat software that's more general and see how Design Expert would handle it, or Stati 360. So I'll leave you with this. We've got some references that, of course, I would have to recommend. I'm biased again as the main author, primary author of these books. But the one that I'd recommend for the existing data is this RSM Simplified. There's a whole section on the Longley data that I mentioned earlier in the presentation. And then, of course, we've got really excellent training. I'm one of the teachers. Modern DOE for process optimization would be a good one to cover factorial and RSM. The RSM tool is the one that you're going to use a lot for existing data for process. And then, you saw my success in dealing with the fuel rod binder using a mixture model, and that's covered in this mixture design for optimal formulation. And we can, do some tailoring. We've got specialized classes for pharmaceutical, oil field services, just all kinds of different things. So if you're interested in that, contact our workshops team via this email. And that's about it. I'm getting pretty close to the end here. I'm just going to take a quick look at chat and see if I have anything, questions. Okay. Can you please send the link to the PowerPoint after the presentation? Marissa had to leave early. So she'll be able to find that, and you will, in the website, we'll post up the slides and also a recording. and I will keep this up and I'll get back to Marissa directly. And Rebecca says, wonderful presentation. Thank you. Thank you very much. I appreciate that. And if there's any further questions, just a couple minutes here. Very useful and valuable. Thanks, Wolfgang. You're welcome, Aruna. Okay. All right. So I tell you what, I'm going to just go ahead and wrap it up. I do appreciate your goodbyes and thank yous, Marcus, and so forth. If you think of anything that you'd like to ask, you've got my email here, mark@staddies.com. Feel free to send any questions into me. But beyond that, good luck with your existing data. All the best. Take care now. I'm going to say goodbye. Bye-bye.